Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In our last lecture, we are through the discussion on interrupt-driven I/O. The input could be connected to the CPU through interrupt, and so could be the output. In the last lecture, we discussed two examples. One example for an input device, or it could be multiple input devices connected to CPU through an interrupt. For this case, we considered our example processor SRC. For the second case of output, which is basically a printer, we used a Centronics interface and Falcon A processor. We went through a number of flowcharts and the assembly programs for both these examples. For both of these examples, the basic concepts are similar. We said that whenever an interrupt is invoked by either an input or an output device, the main program which is running, that is completed as far as the instruction at hand is concerned, then the environment is saved, and somehow or the other the address is available to the CPU for the interrupt service routine. The control is given to the interrupt service routine, and then after the execution of the interrupt service routine, the control is given back to the main program. Now, in the examples which we discussed, we assumed very simple cases, whereby only there was one interrupt at a time. What happens if simultaneously a number of interrupts are invoked? On one bus, there would be many I/O modules which are connected. For example, a hard disk could ask for data transfer, or a monitor would be available for outputting, and if we have simultaneously more than one interrupt, what needs to be done? Which particular interrupt should be handled by CPU? Now, we discussed different mechanisms. Particularly, we said that we could have either a software polling if there are more than one interrupts. A software subroutine could be initiated to look into and ask which particular device initiated an interrupt, and then there could be some mechanism of priority assignment. The second mechanism which we talked about was a daisy chain. In the case of daisy chain, the priority is inbuilt. The device which is nearest to the CPU would get the highest priority. However, this may not be a very good solution. The devices which are away from the CPU may not be handled or may not get an access for a long time. I hope you remember in one of our earlier lectures, we just defined that there are certain deadlines which would be required to be met for different I/O devices. A particular I/O device may not wait too long, otherwise it might become irritating for the user. So therefore, some sort of mechanisms should be evolved so that different devices do get access and get a service. This could be done by different ways. One of the concepts could be that of nested interrupts. The concept in the case of nested interrupts is very simple. Interrupt service routine in itself is a program. We say that, well, if an interrupt service routine is being serviced, and in between another device asks for service or it initiates an interrupt. Now, if that particular device has a higher priority or needs attention, then we can just save the environment within the presently running service routine and then give a control to another service routine corresponding to a higher priority device. And after that service routine is finished, then we come back to that service routine. Now, this concept could be further extended and there could be a nest of the interrupts. So within an interrupt, we get another interrupt and that could be repeated X number of times. And this is what is called a nested interrupt. Now, we could assign different priorities to different devices and we can define different bits corresponding to the priority. You can just imagine a register and different bits correspond to different devices. So just by default, we say that a device which corresponds to the most significant bit in that particular mask corresponds to higher priority, and on the right side, that is the lesser significant bits would correspond to the lesser priority. And we could have either through software or maybe through hardware, we could resolve and see whether we need to pass on the control from one particular device to another. So if we are having a critical phase of a program, we might disable all the other interrupts till we are done with that particular interrupt. So these decisions could be made by the programmer in a particular service routine which is being executed. Let us look at some of the concepts of the nested interrupts in the next slide. In an interrupt I/O system, the deadlines put restrictions on how long interrupts may remain disabled. These deadlines also establish a priority among interrupt requests. Devices with shorter deadlines should be acknowledged first. The priority established by a daisy chain acknowledgement signal only partially addresses the problem. If devices with shorter deadlines are placed closer to the processor in the chain, they will be acknowledged first in case of simultaneous requests. However, if a slower device interrupts just before one with a shorter deadline, the interrupts may be disabled to handle the slow device for longer than the deadline allows. The solution is to allow high priority devices to interrupt lower priority handlers. An interrupt handler is just a program, and as such, its state can be saved and restored to allow it to be resumed where it was left off. This is only necessary that interrupts be enabled at some time during the interrupt handler execution. A system of interrupts that allows an interrupt handler to be interrupted is known as the nested interrupts. Interrupts must remain disabled during critical sections of the interrupt handler subroutine. A critical section could be a code sequence in the routine during which a second interrupt would interfere. As an example, in the SRC processor, the interrupts must be disabled until the interrupt registers IPC and II registers have been saved with the instruction save interrupt. Devices of lower priority then the one being handled would also be disabled before enabling interrupts. The general structure of a nested interrupt handler involves the following steps. The first step is to save the state that is changed by the interrupt response. In particular, for the case of SRC, we need to save the contents of registers IPC and II. Secondly, disable the low priority interrupts. Then we re-enable exception processing. That means the internal interrupts are enabled. Then we service the interrupting device, and again we disable the exception processing. Then we re-enable the low priority devices and restore state involved in interrupt response, that is, bring back the contents of registers IPC and II. Finally, return to interrupted program and re-enable exceptions. Much of the implementation in a nested interrupt system is a matter of software design. However, there are places where hardware support would make the system more efficient. The steps 2 and 6, which means disabling the low priority interrupts and re-enabling the low priority devices, may take a lot of time. And if it is done through software, the overall structure of the program would be slower. Hardware support for this priority disabling would be desirable. Just to understand what needs to be done, we consider a collection of I/O device interrupts which enable some of the bits of a bit vector, usually called an interrupt mask. We order these bits in such a way that for high priority devices we have the right end, and those for the low priority devices we have the left end. That is, if the device J interrupts the correct configuration of the mask while executing device J's handler as shown in the slide, then device J and the low priority devices are disabled and high priority device is enabled. The priority mask, which indicates different bits in a register, should actually be distinct from the individual which enables, because some devices may be disabled for reasons having nothing to do with the priority. For example, the device is off or it is in error. The value of a mask of the preceding priority forms the entire interrupt level, which is J for the current handler. The interrupt level mask should also differ from a simple connection of enable bits in another regard. Most of these devices should really be equivalent with respect to priority level. For example, all disk devices of a given type should have one priority, which is higher than that of all keyboards. Within the group of devices of the same priority, a daisy chain acknowledgement could still be utilized, or we could have an arbitration mechanism. However, the order of devices on the chain is not important within the group. The figure shows one of the possible arrangements of a priority interrupt system. In this case, we have M, which is 2 raised to power k groups of devices. Each group has its own wired or request, and acknowledge corresponds to a daisy chain. The priority system has a register to store the current interrupt level. The priority encoder outputs the binary index J of the lowest numbered requesting that which is asserted as an input. This index is compared with the current level, and if it is smaller, an interrupt request is sent to the process. When the processor acknowledges the request, the current level is set to the level of the new request, and as a result, an acknowledge is sent out on the daisy chain with acknowledge J. Please note, it is not shown in the figure how the mechanism for saving the previous interrupt level and restoring it is done. This can be done using a push-down stack. The depth of the stack is limited by the number m of the priority level. The figure shows the priority interrupt mechanism as a separate subsystem. However, different processors may use different priority mechanisms which might be built into the processor. As an example, the Motorola Series 68000 provides 7 levels of priority interrupts. The priority resolution is a part of the processor architecture. A separate chip may be available along with the CPU for resolution of the priority. By now we have realized that interrupt-driven I/O approach has significant advantages over programmed I/O. Firstly, the processor, the CPU, does not waste a lot of time on just interacting with the device and finding out its status. The device, the peripheral device, only invokes the CPU or initiates an interrupt only when it is ready to transfer data. So thereby a lot of time is saved. Now thirdly, we also notice that the interrupts could be enabled or disabled. So therefore, at some point of time when CPU would not like to be interrupted, it could disable the interrupts. Finally, we have seen that through a nesting process, we could define different priorities to different devices, and the low priority devices could be interrupted by higher priority devices. Through this mechanism, the interrupt-driven I/O is a much better mechanism as far as the programmed I/O vis-a-vis programmed I/O. We would now illustrate these concepts and compare the programmed I/O with the interrupt-driven I/O with the help of some numerical examples. These numerical examples would give you more insight into the performance parameters of the CPU and I/O communication. Let us have some of these examples as numericals. As a first example, we will consider 3 devices connected to the same bus. We have a hard disk with a very fast transfer rate. Secondly, we could have a floppy disk. And thirdly, we consider an example of a keyboard. Now, on one end, we have a very slow device, and on the other hand, we have a fast I/O device like hard disk. Now, with some given figures in the next example, we would see that first we use polling mode, and it is an example of a programmed I/O. We would see the utilization of the bus by different devices, and also see that what could be the waiting time or what could be the polling frequency which could be desirable for different devices. Let's have the figures for this example. Assume that 3 I/O devices are connected to a 32-bit 10 MIPS CPU. The first device is a hard drive with a maximum transfer rate of 1 megabyte per second. It has a 32-bit bus. The second device is a floppy drive with a transfer rate of 25 kilobytes per second, however, over a 16-bit bus. And the third device is a keyboard that must be polled 30 times per second. Assuming that the polling operation takes 20 instructions for each of the I/O devices, we need to determine the percentage of CPU time required to handle each device using polling mechanism. The hard drive can transfer 1 megabyte per second, which is equivalent to 250 kilobytes of 32-bit word each in 1 second. Thus, this hard drive would be transferring the number of instructions as 250 into 2 raised to power 10, where 1K corresponds to 2 raised to power 10, multiplied by 20. 20 corresponds to the number of instructions for the I/O device. This corresponds to 5, 12 and 4 zeros, which means 5.12 mega instructions per second. And therefore the percentage CPU time utilized by the hard disk would be 5.12 divided by 10, which is 51.2%. Now we consider for the floppy disk. The floppy disk can transfer 25K divided by 2, which is 12.5K half words per second. It should be polled with a slower rate as compared to the hard disk. The number of CPU instructions required in this case will be 12.5 into 2 raised to power 10. We will use 1K as 2 raised to power 10 multiplied by 20, which is 256K instructions per second. Therefore, the percentage utilization of CPU time in this case turns out to be only 2.56%. For the keyboard, the number of instructions required is 30 multiplied by 20, which is 600 instructions per second. Therefore, the percentage of CPU time spent for the keyboard is just 0.006%. It is clear from this example that while it is acceptable to use polling for a keyboard or for a floppy drive, it is very risky to use polling for the hard drive. In general, for devices with high data rates, the use of polling is not suggested. Let us now consider another example. The example reads, what should be the polling frequency for an I/O device if the average delay between the time when the device wants to make a request and the time when it is polled is to be at most 10 milliseconds. Part B says, if it takes 10,000 cycles to poll the I/O device and the processor operates at 100 megahertz, what percentage of the CPU time is spent in polling? Part C reads as, what if the system wants to provide an average delay of 1 millisecond instead of 10 milliseconds? Let us look at the solution. For part A, assuming that the I/O requests are distributed evenly in time, so we use a uniform distribution. The average time that a device will have to wait for the processor to poll is half the time between polling attempts. Therefore, to provide an average delay of 10 milliseconds, the processor will have to poll every 20 milliseconds, which means a polling frequency of 50, that is 50 times per second. Part B, we need to calculate the percentage of CPU time spent in polling. If each polling attempt takes 10,000 cycles, then the processor will spend 500,000 cycles polling each second. The percentage of CPU time spent in polling is then 0.5 into 10 raised power 6, which is the number of cycles for polling divided by the frequency, and in this case clock has 100 megahertz, so 100 into 10 raised power 6 in the denominator, that corresponds to 0.5%. So we have 0.5% as the CPU time which is spent in polling. Part C, we see that to provide an average delay of 1 millisecond, the polling frequency must be increased. The processor will have to poll every 2 milliseconds instead of every 20 milliseconds. So this would mean that the frequency would be increased from 50 to 500 times per second. Therefore, this will consume 5 million cycles for polling. The percentage of CPU time spent then on polling would become 5% instead of 0.5 in part B. Let us look at the third example, which corresponds to a printer. We need to calculate what percentage of time will a 20 MIPS processor spend in the busy wait loop of an 80 character line printer when it takes 1 millisecond to print a character and a total of 565 instructions need to be executed to print an 80 character line. Assume that 2 instructions are executed in each polling loop. Looking at the solution, out of the total 565 instructions executed to print a line, 80 multiplied by 2, which is 160, are spent for polling because we need 2 instructions per poll. For a 20 MIPS processor, the execution of the remaining 405 instructions would take a time of 405 divided by the MIPS 20 into 10 raised power 6, which corresponds to 20.25 microseconds. Since the printing of 80 characters takes 80 milliseconds, therefore 80 minus 0.02025, which is 79.97 millisecond of time, is spent in the polling loop before we get to the next 80 characters to print. This is 99.96% of the total time, which is tremendous. And this example just illustrates that due to the mechanical nature of the printer, a lot of time would be required in printing, and therefore we are wasting a lot of CPU time. CPU would be just waiting for printer to be ready for the next queue. In all these 3 examples, we could notice some important factors. The first important thing is we should see and keep in mind what is the speed of an I/O device. The high-speed devices may not be prone to polling, whereas for slow devices, polling could be an option. The printer, for example, is very slow and takes a lot of time in printing. In such a case, keep on polling would not be a good solution, and a lot of CPU time would be wasted. Now, the device may not be ready for the next data to be printed till we just are finished with the first one. So it depends on a particular situation. However, for all these cases, one thing is clear, that polling may not be an ideal solution. In the next examples, we will see the situation with the interrupt-driven I/O examples. Now, in the next example, we consider a 20 MIPS processor with several input devices attached to it, each running at 1000 characters per second. Assume that it takes 17 instructions to handle one interrupt. If the hardware interrupt response takes just 1 microsecond, what would be the maximum number of devices that could be handled simultaneously? So this example illustrates the situation with interrupt-driven I/O. A service for one character requires 17 instructions, which corresponds to just a time of 17 divided by 20 into 10 raised power 6, and there is 1 microsecond extra time for interrupt response. This amounts to 1.85 microseconds. Since each device runs at 1000 characters per second, therefore 1.85 millisecond of handling time is required for each device every second. Therefore, the maximum number of devices that could be handled simultaneously would be 1 over 1.85 into 10 raised power minus 3, which corresponds to 540 devices. In this example, we have all devices identical, just for the sake of illustration. In the next example, we see the different devices connected to the same bus using interrupt. The example reads, assume that a floppy drive having a transfer rate of 25 kilobits per second is attached to a 32-bit 10 MIPS CPU using an interrupt-driven interface. The drive has a 16-bit data bus. Assume that the interrupt overhead is 20 instructions. Calculate the fraction of CPU time required to service this drive when it is active. Since the floppy drive has a 16-bit data bus, it can transfer 2 bytes at one time. Thus, its transfer rate is 25 divided by 2, which is 12.5 kilo half words, 16 bits each. So total word is 32-bit, and in this case 16 bits correspond to half word. This corresponds to an overhead of 20 instructions, or 12.5k into 20, which is 256k instructions per second. In the next example, we consider a processor with a 500 megahertz clock, which requires 1000 clock cycles to perform a context switch and start an interrupt service routine. Assume that each interrupt takes 10,000 cycles to execute the ISR, and the device makes 200 interrupt requests per second. Also assume that the processor calls every half millisecond during the time when there are no interrupts. Further assume that the polling at I/O device requires 500 cycles. Compute the following. A. How many cycles per second does the processor spend in handling I/O from the device if only interrupts were used? Part B. What fraction of the CPU time is used in interrupt handling for part A? C. How often should the processor poll so that polling occurs with the same overhead as interrupts? Looking at part A, the device makes 200 interrupt requests per second, each of which takes 10,000 plus 2 into 1,000 for context switching to the ISR and back from it. That makes a total of 12,000 cycles. Therefore, a total of 200 multiplied by 12,000, which is 2.4 million cycles per second, are spent in handling I/O using interrupts. In part B, we convert this data into percentage of the processor time used in interrupt handling. Therefore, we just divide 2.4 million by 500 million, which turns out to be only 0.48%. Now in part C, the interrupt overhead is given as 1,000 cycles per second for a context switch to the interrupt service routine and 1,000 cycles per second back from it. This means a total of 2,000 cycles per second. With 200 interrupts per second, this amounts to 400,000 cycles per second. The polling overhead is 500 cycles per second. Thus, for the same overhead as interrupts, the polling operation should be performed with 400,000 divided by 500, which is equal to 800 times per second, or every 1.25 millisecond. Now these three examples have illustrated some calculations with interrupt-driven I/O. We could also combine the interrupt with the programmed I/O. And in the last example, we have seen some figures where polling as well as the interrupt is combined together. Now, the conclusion definitely is that we have an interrupt-driven I/O which is more efficient than the programmed I/O. We have illustrated this with the help of 6 examples. The first 3 examples covered the polling, or which corresponds to a programmed I/O, and the remaining 3 examples introduced to the calculations with interrupt-driven I/O. Now, whether we use programmed I/O or interrupt-driven, one thing is clear: CPU is always involved. Whether it is an interrupt or it is a programmed I/O, when there is an exchange of data between the peripheral device and the memory, it is under the control of CPU. The bus cycle is controlled by the clock of CPU. So therefore the CPU is involved. So in cases where we have a lot of I/O activity, whether it is done through programmed I/O or it is done through an interrupt-driven I/O, it might not be an excellent or an ideal solution. We will now look into another possibility, and this we have discussed with reference to the memory subsystems, and it is called a direct memory access. In the case of direct memory access, we could exchange data without the control of the CPU. the similar concept would now be used for the I/O subsystems. If we want to change or exchange data from one I/O device to another I/O device, or from I/O device to the memory, from one part of the memory to another part of the memory, we could utilize the concept of DMA. Let us now look at this concept of DMA. Direct memory access is a technique whereby the CPU passes on its control to the memory subsystem or one of its peripherals, so that a contiguous block of data could be transferred from peripheral device to memory subsystem, or from memory subsystem to peripheral device, or from one peripheral device to another peripheral device. What is the advantage of using DMA? The transfer rate is pretty fast, and conceptually you could imagine that through disabling the tri-state buffers, the system bus is isolated and a direct connection is established between the I/O subsystem and or the memory subsystem. And then the CPU is free, it is idle at that time, or it could do some other activity. So therefore the DMA would be quite useful if a large amount of data needs to be transferred from, as an example, from one hard disk to a printer, or we could fill up the buffer of a printer in a pretty short time. So as compared to interrupt-driven I/O or programmed I/O, DMA would be much faster. What is the consequence? The consequence is that we need to have another chip which is a DMA controller. Now DMA controller could be a CPU in itself, and it would control the total activity and synchronize the transfer of data. DMA could be considered as a technique of transferring data from I/O to memory or memory to I/O without the intervention of CPU. CPU just sets up an I/O module or a memory subsystem so that it passes control and the data could be passed on from I/O to memory, or from memory to I/O, or from within the memory from one subsystem to another subsystem without intervention of CPU. After this data transfer is complete, the control is passed from I/O back to CPU. We will just illustrate the advantage of this DMA with the help of a very simple example in the next slide with reference to our famous SRC processor. Now if we write instruction load within square brackets 2, within square brackets 9, we would like to mean that transfer data from location 9 in the memory to location 2 in the memory. This instruction, however, is illegal and is not available with SRC processor. The symbols with square brackets 2 and 9 represent memory locations. If we want to have this transfer to be done, 2 steps would be required, and the instruction would read as load R1, 9 in square brackets and store R1, 2 with square brackets. Thus, it is not possible to transfer from one memory location to another without involving the CPU. The same applies to transfer between memory and peripherals connected to I/O ports. For example, we cannot have out with square brackets 6 data port. It has to be done again in 2 steps. First load R1, 6 in square brackets, that is, fetch the contents of memory location 6, place it in register R1, and then out R1, data port, and the contents of R1 would be passed on to data port. Similar comments apply to the in instruction. Thus, the real cause of the limited transfer rate is the CPU itself. It acts as an unnecessary middleman. The example illustrates that in general, every data word travels over the system bus twice, and this is not necessary, and therefore DMA in such cases would be pretty useful. The DMA approach is to turn off, that is, through tri-state buffers, and therefore electrically disconnect from the system bus the CPU and let a peripheral device or a memory subsystem or any other module or another block of the same module communicate directly with the memory or with another peripheral device. This would have the advantage of having higher transfer rates, which could approach that of limited by the memory itself. The disadvantage, however, would be that an additional DMA controller would be required, and that could make the system a bit more complex and expensive. Generally, the DMA requests have priority over all other bus activities, including interrupts. Today we have discussed, with the help of some examples, the interrupt-driven I/O devices. We have seen that in most of the cases, the interrupt-driven I/O has an edge advantage over the programmed I/O. However, we started our discussion with direct memory access, which could be more efficient than both programmed I/O as well as interrupt-driven I/O, particularly in cases where large blocks of data are to be transferred to and fro from peripheral devices to memory or vice versa. And DMA technique is pretty efficient in such a situation. We will continue our discussion with DMA in the next lecture. That's all for today. Till next time, Allah Hafiz.